So up to this point in our development of techniques for differentiating, we have focused solely on functions. For instance, if y is a function of f, or x, sorry, so I'll say f of x, then we know the differential of y is f prime of x dx. However, there is absolutely nothing in our differential rules that require y be explicitly a function of x. So if we scroll down, take a look at our rules as we've collected them so far, we see that we know that the differential of a constant is 0, that constants factor out of the differential operator, that the differential operator distributes across addition and subtraction. We have a rule for dealing with multiplication, for division. We've got our power rule. We've got all of our trig rules. We have, as we developed in the last section, rules for exponentials and rules for logarithms. But none of these rules require that we've got a function per se, like y equals f of x. Y and x could be related in a way, but not be functions explicitly. So let me kind of give an example that will hopefully make things clear. So let's say we have the simple relationship between x and y, that x squared plus y squared is 1. I hope that you can easily recognize this as being a circle with radius 1 centered at the origin. And if we were to plot its graph, it would look something like this. And we could ask the question, at a point P, what is the equation of the tangent line? So even though y is not explicitly a function of x, it still has a graph, and we can still ask what is the slope of the curve at that point P. And since derivatives and differentials are all about the infinitesimal, we pull out our handy infinitesimal microscope and we can zoom in. And of course, as we know at the infinitesimal level, our curve, the circle, looks much more like a line, and the differential of y measures the change in the y direction. The differential of x is our change in the x direction, and then we finally have, right, as we always do, that our slope is the ratio of those two changes, dy dx. So if, say we're at the point, and it looks like it's about there, at the point, say, root 2 over 2, root 2 over 2, right? This is our point P, and we want to know what is the equation of the tangent line. So we've got our point, we need to calculate our slope. And I could technically solve this. I could say, y is equal to plus or minus the square root of 1 minus x squared, and compute the derivative of y with respect to x using the power rule and the chain rule inside. And of course, we would have to decide which sign to use. We'd have a plus or minus. And in the picture, we can see, oh, well, here y is positive, so we'd use the positive one. However, there's another way called implicit differentiation, in which we can get our handle on the same thing. It's easier. And this equation was nice because we could solve for y, but there will be plenty of equations in which it is not possible to solve for y. Similar to the instance of when we were looking at inverse functions, it's not always possible to find the inverse, but we can always define what the slope of the inverse function would be, even if you don't have the function explicitly. So how do we go about it? So let's get some room here, and we set up, I'll rewrite the equation. We know that x squared plus y squared is equal to 1. Now this equal sign is key, and in mathematics, this is always something that is very useful because if I've got an equal sign, it means that this relationship on the left-hand side is identical to 1. Let that sink in. That even though I've got variables over here, that if I put an x and y that lives on the circle, then its relationship is that it's equal to 1. Well, we can take that even further and say, well, they're equal. That means their differentials are equal. So I can take the differential of the left-hand side of this whole expression, and it's got to equal the differential of the right-hand side. So writing that out, I've got that the differential of x squared plus y squared, which is identically 1 by the equation, so it's got to be equal to the differential of 1. So coming back to our rules of differentiation, we know how the differential behaves across addition. It just distributes, right? So this differential operator will move across the addition sign, giving us our dx squared and dy squared. And on the left, or on the right-hand side, the differential of a constant, the differential of 1, is a big fat 0. So adjusting our equation appropriately, this tells us that the differential of x squared plus the differential of y squared is equal to 0. And now we apply our power rule. So power rule says that the power comes down, becomes our new coefficient, and reduces by 1. Similarly here, the power 2 comes down, becomes our coefficient, and reduces by 1. So we rewrite the left-hand side as 2x, and we're taking differentials here, so we've got to hold on of the variable we're taking the differential of, so it's 2x dx. And here, this will be 2y dy. And the whole equation is equal to 0. And what we have now is a relationship between dx and dy. And so let's go back and see what we're looking for. Remember, we want the slope, which is the ratio of dy dx. So we want to solve what is dy divided by dx equal to. So I will bring my dy, or actually I'll keep it on the left-hand side, and I can divide, or actually let's do it easier this way. Let's subtract. We'll bring this over. So I get that 2y dy is equal to negative 2x dx. And I want to solve for dy dx, so I divide both sides by, say, dx. And, right, because this is just an algebra expression now. Yes, we've got variables that we're not used to seeing from algebra, but dx is simply a new variable that we work with in calculus. And so I get that 2y dy dx is equal to negative 2x. And I want to solve for dy, so I will divide again by 2y, and this by 2y, giving me the relationship that dy dx is equal to negative x over y. This is our relationship, the slope at any point. Notice I don't have to determine whether y is in the top half of the circle or the bottom half of the circle like I would have in my equation here, where I would have decided is y positive or is y negative. I solve this relationship, and I know implicitly, or explicitly, that the differential of y with respect to x, the slope of the curve at any given point, is equal to the ratio of the negative x component divided by the positive y component, or negative x divided by y. And so at the point that I'm interested in, at the point root 2 over 2, I can calculate it, that the slope of the curve dy dx at the point x, y is equal to root 2 over 2, root 2 over 2, that this is equal to, so I'm going to put root 2 in for x and root 2 in for y, since they're actually the same here. So it's going to be negative root 2 over 2 divided by root 2 over 2, which is equal to negative 1. So our slope, back to the original problem, we want to know the slope. So the slope at this point is negative 1. And then finally our equation of the tangent line, since that's what we were looking for, the equation of the tangent line will be y minus our y-coordinate, which is root 2 over 2, is equal to negative 1 times x minus root 2 over 2. That's the equation of our tangent line at the point root 2 over 2, root 2 over 2. So again, let's recap. What did we do? We wanted to know the differential of y with respect to x. We wanted to know dy dx. And we had the relationship x squared plus y squared equals 1. And so we took the differential of both sides and we used our known differential rules to get ourselves to an equation in which we just had dx, dy, and then maybe some x's and y's running around. We then solved for dy dx. So we wanted the expression dy dx to appear. The easiest method is to get all the dy's on one side, all the dx's on the other side, and then divide. And then finally, any straggling or remaining variables that were not dy dx, we brought to the right-hand side, and we got our equation.